Yeah, thanks again for coming. I'm sure there'll be a few more people that roll in here as I get started. The talk today, a couple disclaimers. First, I like to move around a lot, so I'm sorry for the camera people. And I hope I don't make you dizzy. That's the way I like to do it. I've been traveling a lot the last 2 weeks, so definitely feeling a little jet lagged, but I'm gonna give this maximum energy. So hopefully you're a kind audience. So hypervisor hierarchy, that's what we're here to talk about. And the Zen project, and specifically why architecture matters for performance, security, and flexibility. There's lots of ways to build a hypervisor, lots of ways to do virtualization, and this talk is really about presenting some of the differences and the different technologies that exist, and why I believe that Zen is well positioned to be the best hypervisor. Depends on the use case, so I'll present those alternatives as well. So let's get started. I think I have a clicker here that I set up. Yeah, that's me. A couple links on there. LinkedIn is probably the easiest way if you want to connect with me. Go all the way to connect. Don't just follow. Connect with me on LinkedIn. Be happy to chat with anybody. I'm the community manager for the Zen project. I started that role I think in March, so I'm fairly new to the project, but got enough time there to make this presentation and be excited about it. This is a new presentation for me too, so hopefully this goes well. I also teach at the local university where I live in France. Teach technology and software development. I love learning and transmitting knowledge, something that I really love. If you want to follow along, be more than happy that you do. You can scan that QR code. If you do so, one of the fun things you can do, sorry, I'm mumbling my words. I think that's the fatigue hitting me, but you can follow along, and you can even put like emojis on here while I'm talking. If you don't like what I'm saying, you can put exploding heads on here. It lets me know that you're not sleeping yet. It could happen later. So more of that, the better. I love interacting with the audience. Confetti. If you put too much confetti on there, I can't read the slides. That's not a challenge. Please don't. A limited confetti is always appreciated. I built this presentation framework. That's a different talk. And I haven't enabled the button to throttle the confetti, so be warned. Let's jump right in. So there is a hidden layer to your applications, to your workloads, powering those workloads. You can probably guess what that hidden layer is. It's going to be hypervisors, right? And hypervisors are a technology that's invisible until something breaks. And the metaphor I wanted to use for this presentation is traffic. Thinking of traffic control systems, streets, city layout. I believe this is a photo of Manhattan. So I'm thinking of American cities that are fairly modern, built in grids, where traffic flows easily, put that in quotes, always depends on how much traffic there is. So I'm gonna go back to this metaphor throughout the slideshow. You'll probably be sick of it by the end of the presentation, but I was looking for something to really illustrate the differences and the different types of hypervisors and finding a metaphor that really sticks, and this works. So before we jump into the different types of hypervisors, a quick review of virtualization. I call virtualization 101. I use my clicker, but I keep coming back to my computer. So what is virtualization? Why do we need virtualization? We're thinking about running multiple VMs, or multiple cars, to stick with our metaphor, sharing the same lanes on a road or the same highways, thinking about the hardware, right? The same infrastructure. So multiple VMs on the same infrastructure. And we can have multiple OSs on a single physical machine. So I know I'm not revealing any groundbreaking information there. So I'm just going to expand this so I can see the slides better on my screen. And hypervisor, as I prepped you already, I'm going to use this metaphor. It's kind of like traffic control. How do we control the traffic? How do we control the workloads in a way that's safe, that's efficient, secure, and flexible? So let's dive into that. Why do we need hypervisors? Well, the first part is isolation. Because if we end up with a whole lot of craziness everywhere, traffic can't circulate. It can't happen. We need isolation in terms of dedicated lanes to securely separate those workloads. Specifically, I got a lot of exploding heads, so hopefully you're not angry at my presentation already. Specifically, one of the things I'll talk about now is that Zen is growing in the automotive and industrial space. It's much, oh, I think I clicked a button by accident, there we go. It's much more cost effective to use one computer, one board inside an embedded device, or automotive, maybe avionics soon, with multiple cores in the processor, and run multiple machines at the same time. And so one of the things we talk about isolation is, if one virtual machine crashes, do they all crash? That would be horrible in a car, right? If you have mission critical workloads running next to the infotainment system, playing your favorite songs in Spotify, that would be horrible if one would crash the other. So that's what I'm talking about with isolation, minimizing that crash impact and keeping the separation of concerns separate. Efficiency, right? So you have that multi-core CPU, a lot of RAM, a lot of different I/O resources. How do you use those efficiently? How do we get the most bang for our buck? We're building things at large scale. We need to cut costs wherever we can, right? That's a common theme that we all hear about. So how do we get the most efficiency out of those workloads? And the hardware utilization is part of that. And the cost, right? How do we be efficient about cost? Again, I know this isn't groundbreaking, but I'm building up to something. So flexibility, we need to reroute workloads when needed. So if you think about maybe a classic virtualization use case is going to be cloud services, spinning up VMs, or different serverless functions or containers that are going to be based on VM workloads. How do you reroute workloads when needed? How do you add or remove resources? That's another interesting use case. If we go back to enterprise use cases, you might have either running in the cloud or on-site servers, and folks can connect to a virtual machine to do work. I've worked at development shops where we worked on VMs, and also those in-house services, those back office services are often running on VMs. So how can we add and remove resources? That's where the hypervisor comes in, is creating that flexibility and the possibility to move workloads when needed. So this is why hypervisors matter. They're that control layer that makes virtualization safe and practical. Now, you're probably asking yourself, isn't that why we have containers, right? It's 2025, Cody. Like, containers have been around for a while. Why do I care about VMs in this day and age? Well, there is some interesting differences that are really important today in the modern era in 2025. So talking again about those separate protected lanes is my metaphor that I'm leaning on here. And a VM is going to emulate a full computer, right? You get the hardware, you have access to actual I/O devices, the operating system, the apps, that's built into each VM, where if we compare that to a container, you're running processes. Sure, when you build your container, you choose which distro it's based off of, but that process is running in the host operating system on a container-based system. So if the host operating system fails, all the processes fail, all the containers fail, and there are some security concerns with running in containerized services because it's the kernel that's creating that isolation. It's not built into the architecture from the core. So there are ways, we've all seen security related issues around containers that have been fixed, but the nature of the beast is that there's less isolation in containers. But containers are faster, generally speaking, lighter, less isolation. We now have like micro VMs, so the faster piece, they're still fast, right? But maybe that'll change one day. But obviously, if you're running the full operating system and all the apps in a VM, it can never really compare directly to containers. Moving on. So let's talk about design choices when we're building a hypervisor and doing virtualization, because not all cities are created equally. I'm coming back to my city metaphor and traffic control metaphor. There are some specific design choices that are interesting. If we talk about cities, road design shapes the traffic flow, right? It's the same for hypervisors. Like here's another shot, I think, of Manhattan. Thinking of a purpose-built grid. I live in France now, but I'm American. But in most American cities, streets running like east to west are going to be numbers, and streets running north to south are going to be alphabetical letters, often named after presidents, but that's just a weird American thing. And if you're at 82nd and Jefferson, if somebody tells you I'm located at Lincoln and 2nd Street, you can tell just by looking at the street signs how to get to your destination. You don't have to pull out a map. You don't have to pull out a GPS. Good luck doing that in Europe. I live in France. Good luck figuring out where you need to go. If you don't know the roundabouts, where to go up and down, under the bridge, over the railroad tracks, around the train station, good luck getting where you need to go without a GPS. You just have to know, right? You can follow those signs, but they'll take you on that maze. So type 1 hypervisor is purpose-built, just like modern cities are often attempting to do. And you have direct routes, and it's easy to scale, right? We can create roads that are wider in the center of the grid and have smaller routes in the residential neighborhoods, but it's all based off of this grid. And it's built for cars from the ground up. That was its purpose from the beginning. So if we compare that with a type 2 hypervisor, you can read this on Wikipedia too, the type 1 and type 2. This is the official theory behind the differences in hypervisors. It's a layered, old world city. I'm thinking a European city with narrow alleys, and winding streets. So it's been retrofitted, and it wasn't designed for modern traffic. So we got that van or truck trying to drive through that really small street, right? It can do it, but that street was never made for that. It was made for people walking, or maybe some horses or something, right? 200, 300, 500 years, 1,000 years ago, depending on what city you're in. So a type 2 hypervisor is this retrofitted old city, has extra intersections, detours, it's less efficient. And the difference is whether the hypervisor sits directly on the hardware, like type 1, or if it's on top of another OS. We'll dig into that later. When I say that on top of another OS, I'm thinking about VirtualBox or the other virtualization technologies you can run on your computer, Parallels if you're using Mac. That's running on top of your OS. So your processor probably has, in your OS, has some interfaces that allow for emulation, and those processes are running on top of another OS. So that's a type 2 hypervisor. Now, the lines can get blurry sometimes. There's this concept of a hybrid type 1 hypervisor, and it's just like some cities are a mix of old and new. You might have the old center of a city and then a grid on the exterior. You might have ring roads, périphérique in French, roads that go around the exterior of the city, trying to build on something modern into something that was old. These ring roads around medieval centers. It looks modern, but those legacy layers are still there, and they constrain the flow. So, drum roll, KVM, Camus, the most common hypervisor and virtualization technology in Linux is what I call a hybrid type 1 hypervisor. Because KVM runs on modules running in the kernel, so you need to have a full Linux operating system in order to run KVM. I have some comparisons here. Here we go. So on the left, we have Zen, a true type 1 hypervisor. On the right, we have KVM, a hybrid type 1 hypervisor. We'll start at the bottom of the diagram. The firmware and the hardware, it's probably the same in both cases. We have the Zen hypervisor on one side, and the Linux kernel and the KVM kernel module running on the KVM side. And then we'll get to this in a little bit more detail. On Zen, we have what we call DOM 0, so domain 0. This is the control domain. It's optional. I'll talk more about it in a second, but in embedded devices, automotive, you don't need to spin up new VMs dynamically, right? So we don't need to have that, but it's the interface that lets users or software decide when to add more resources and add more VMs. That's the control domain, DOM 0, so it's gray because it's optional. And that's kind of similar to what we get with Camus, libvirt, systemd on the Linux side, the KVM side. And then, of course, we have VMs at the top. Now, that was just to illustrate the similarities in the two. Now I'm going to draw this to scale. Prepare yourself. It's much smaller on the Zen side. There's really no, this isn't drawn to scale. This is just to illustrate my point that you end up on the KVM side with the huge Linux kernel, the KVM modules, all the operating system pieces, the parts to upgrade the OS that's running that. You have a lot more software included when you're using the KVM side versus on the Zen side, we can get a much smaller impact, a much smaller footprint, and this gray box, the DOM0, that could just go away in embedded use cases. So like I said, it's really interesting for the embedded use case, and it's really interesting when we talk about security, which I'll come back to in a second, but thinking about reducing your attack vector, well, it's much smaller on the left-hand side. So, design choices. Hybrid type 1 hypervisor. I guess I'm just summarizing what I said. I get excited and start saying the slides before they come up. It's heavier. It has a lot of dependencies. It's harder to certify for safety. So as I mentioned, Zen is becoming really important in the automotive space, industrial space, hopefully soon avionics, because there's just much fewer lines of code to safety certify. Like we can't run a hypervisor in a mission critical, a safety critical environment without getting it certified. And I will tell you that Zen is going to be safety certified much quicker than KVM will be because of all the extra software that comes with KVM and the Linux kernel. So that hybrid type 1 is a harder to certify for safety, and it's a slower path, for automotive and industrial adoption. More complexity, harder to certify. And Zen is kind of independent. The hypervisor runs directly on the hardware with that DOM0 being optional in the last diagram. So back to city design and hypervisors. You have kind of this purpose-built hypervisor, Zen, versus something that's retrofitted, and this makes a difference. This makes a difference. There are trade-offs. I hinted at these already a little bit, but let's summarize those a little bit, because how the system shapes the flow is, of course, the case. So security, preventing collisions. We need to have clear lanes, barriers, predictable signals, versus hidden alleys. There's more risk, right? So if you're talking about including a full Linux operating system with KVM, the attack vector is so much larger. There's so much more to get safety certified. Whereas if we go back to performance, this architectural trade-off, there's these direct grids, is my metaphor, right? For consistent speed versus the old layouts of old cities, there's going to be these bottlenecks. And it's kind of the same thing for Zen. Now, Zen is obviously a mature project, which I'll go into later. It wasn't just invented in 2025. It's been around since the early 2000s. We'll dig deeper into that in just a second. Finally, that flexibility piece, I think I hinted at this in the beginning. We have DOM0, which gives you that dynamic lights. So I'm really leaning on my metaphor here. So use your imagination as we go here. It allows you to reroute workloads as needed. It gives you both DOM0, the dynamic control, and you can have DOM0 less. So there's fixed cycles for predictability in the embedded space, where the interrupt latency, so the amount of time between an I/O interrupt and when it gets serviced by the user application, that needs to be predictable, it needs to be measurable, and it needs to be small, ideally. DOM0 less, so having no DOM0, having no control plane to allow you to dynamically add VMs gives you that ability. So this is really interesting in the embedded space. Design determines how safe, fast, and flexible it can be. Okay, I don't need to read these out loud. So finally, let's get to Zen. It's a modern traffic system. Even if it's mature, it's been around for a long time, it's built on these modern principles and these modern concepts. I think I just moved the microphone closer to my mouth. So Zen, mature, modern, and growing. Zen has been around for 20 plus years. It was created in the early 2000s as a research project in the university. But it's mature and still modern at the same time because it was built from the ground up to be type 1 hypervisor running directly on the hardware. There's no reliance on a host operating system as we might see in other hypervisors. At DOM 0 piece, the traffic control center, if you want, gives it the ability to be dynamic and flexible versus a DOM 0 less. Okay, I already mentioned that. Same hypervisor, adaptable to both cloud, large, scalable cloud workloads and for faster, reliable, flexible, embedded workloads. Now, Zen is still at the core of some really important projects. AWS Elastic Compute, the original version, was based off of Zen. Since then, Amazon has designed their own hypervisor in-house. But the original version, which is still out there, still in the wild, Elastic Compute 1, was built off of Zen. And a lot of other cloud and embedded projects are based off of Zen. But it evolves at the same time. Like I said, you have that DOM 0 versus DOM 0 less that lets you adapt Zen if you're going to use it in a dynamic workload versus like an embedded space. It runs on ARM. It runs on RISC-V. So it's super modern at the same time. Also ran on PowerPC, but that's not super relevant for today, but it is run on many architectures. Of course, x86. I have a slide on that later. Like I said, purpose-built. It was a type 1 foundation from the beginning. There was no retrofitting to try to make this appear like a type 1 hypervisor. And there's no detours through other systems. Purpose-built. Okay, I'm driving that point home a little too much. Next, DOM 0, that smart control center is what I'm calling this, which lets you dynamically add and remove workloads. This is great for cloud applications, scalable workloads, dynamic environments. And then we go back, okay, I'm repeating the same slides. I guess I just go through the slides faster than they show up on the screen. I talked about DOM 0 less for embedded, automotive, industrial, that predictable traffic patterns. So Zen is flexible, is the point that I wanted to make here. Whether you're doing something dynamic or something fixed, depending on what your city needs, Zen is there to help. So the design matters, right? That's the point that I really want to make here. That we have this unified ecosystem around Zen. There's one road authority. You don't have competing police officers. There's one authority handling all the hypervisor in the stack. So there's fewer integration headaches. It's secure from the start, right? There's this smaller attack vector that can happen, the trusted computing base, the TCB. So there's fewer accidents waiting to happen. So better fault isolation and easier to audit, which is important in the automotive and avionics space. Hardware alignment. So Zen works with ARM, RISC-V, x86. I guess I mentioned that. So it's ready for the future of traffic. If there's another architecture that comes along, it's ready to be adapted to that. It's built from the ground up to be cross-platform. And it matters. Zen is trusted by huge industry leaders. This year, we welcomed Honda, we welcomed Ford, we welcomed Renesas. We have the members of the Zen project, the advisory board members that steer the project are huge players. Like they know this is the future. If we talk about the automotive space, talking about software-defined vehicles, Zen is there. Zen, these companies are bought into that concept. So I put the logos of all the members on here to show that off a little bit. I'm really proud of the members that we have in the Zen project. It's going places, right? And this has just grown over the last couple of years. And that automotive use case, that's happening now. That's happening now. If you're interested in talking more about that, I'm happy to explain where Zen fits in. If we talk about the automotive space, the AGL, the Automotive Grade Linux project, they use Zen in their reference architecture. You have the hardware, then you have the Zen hypervisor, and then you're going to have some real-time OSs, maybe something for the infotainment system that's built into the stack, and it's Zen that's there supporting that. And these members work together that we have a common foundation that everybody benefits from this secure, flexible, performant base. And we're expanding into industrial and edge systems. It's a fit for many different places because of that flexibility. So design, I mean, we're all tech folks. Obviously, it's not just about day one. It's about long-term flow, safety, and growth. Design isn't just about day one, use cases and ecosystem. So let's get into some more nuts and bolts, some interesting things. Cloud infrastructure, thinking about mega cities, leaning on my metaphor still. So that's one of the use cases for Zen, the high capacity highways, dynamic traffic lights, running in the cloud. Then we have the embedded automotive. I'm just really leaning on these points that I want to make. And in the automotive space, predictability is much more important than flexibility. And that's where we sneak in the DOM zero lists for those fixed light cycles, is the metaphor I was leaning on for this slide. And the research and innovation. So if you want to test new traffic patterns on a solid foundation, Zen is a great place because it's been around for 20 plus years. There's tons of academic research, tons of master's and doctorate theses where the research was done on Zen-based systems. We just recently added to our website a research paper page to the website where folks can put in research papers that were based on Zen. Really proud of the work that's happened there. Zen has just been something incredible in the academic field, academic space. And finally, one system beats fragmented patchwork cities. That's really the point that I wanted to take home from this presentation, is that true type 1 hypervisor, purpose-built, is very important. Now, I want to give a few shout-outs for talking about use cases in the ecosystem. XCP-NG, that's the logo is the rocket here on the right. That's a drop-in replacement for your virtual machine software that you might know about. The most common one starts with VM and ends in where. They changed their licensing setup when it was acquired by Broadcom. It's now very expensive for enterprises to use it. You can use XCP-NG out of the box. It's free. It's based on Zen. It's a turnkey distribution that's ready to be set up on a server for enterprise applications, home labs, lots of different use cases. XCP-NG is a great way to test out, kick the wheels, test out Zen right away. Obviously, if you're building an automotive software-defined vehicle, or something in the embedded world, embedded space, you're not going to be running XCP-NG because it's a distribution that runs Zen in it, but that lets you try it out. The unified ecosystem avoids fragmentation. Very proud of that. What the maintainers have recently done, this is so cool. We have an open GitLab CI that validates everything that happens, all the commits that happen on Zen, they get validated on real hardware. And the fact that it's open, if you work in the industrial space, if you work in the automotive space, the embedded space, you might have a custom board that you're working on, that your company's testing hardware on, software on. You don't have to ship it to a lab. You can connect it to a host computer through the serial port, connect the host computer to our GitLab CI, a few steps in the configuration to make it connect to our CI, and every commit will run on your custom hardware sitting on your desk. This is huge. There's no other hypervisor, open source project that does this. The fact that the CI is open, there's just a few configuration files that add runners into it. It's huge in that industrial space, in the automotive space, because they want to test those boards right away. The faster you can test that out, the changes in Zen, the quicker you can get to market, the quicker you can fix those bugs, the fewer surprises you'll have for later. So the OpenCI, we have a couple pages dedicated to that on zenproject.org. Do check it out. Super proud of that work. And this is a game changer. Talk about embedded use cases. Our partners can plug their hardware into the CI pipeline, do on-site testing. Now, obviously, memberships is what maintains and sustains the Zen project. That's the way that it works. OpenCI ensures everything works across the cloud embedded system. Okay, I already read all these. Sorry, I just talk and I don't actually read the slides. On-site. So, I really wanted to call out also is the road ahead. Your city design, your hypervisor of choice, driving virtualization forward requires the right foundations. Now, the call that I really want to make is you can contribute to the project. Obviously, we're at the Open Source Summit. Zen is open source hypervisor. There's plenty of places to contribute: code, docs, testing, the CI, infrastructure. We have drivers for Windows. We have drivers for other operating systems, Linux, for the guest drivers. Always looking for help if you want to get involved in an exciting open source project, a project that's building, that's growing right now, today in 2025. Zen is a great place to come. And we obviously have an advisory board. I mentioned this. So we have members, voting members of the advisory board that help steer the project. That helps fund the CI. That helps fund the testing hardware. That helps fund the different integrations that we have in the developer time. So membership is key to the way that the Zen project functions. So if you're working in the embedded space, the data center space, come and get involved in Zen. There's many ways to get involved. And membership matters. This ensures the project sustainability and influence. You can have influence on the roadmap by funding features, etc. So obviously the maintainers and the committers, they make the code decisions, but the board drives the project. Always looking for folks who want to get involved. And if you're working at a company that's going to be building a software-defined vehicle or something new in the embedded space, become a member, and I can show you where Zen fits into your architecture and why it's the foundation, that open foundation, the secure foundation that we need. That's the obvious call for open source, right? The more eyeballs on the code, the more secure that code is. So that's the way Zen works. And if you're building something amazing on top of it, make sure that your foundation is solid. So back to city design and hypervisor architecture. We have that type 1 hypervisor. It's predictable. It's that predictable grid that we all know, that we all love. And they have the type 2 hypervisor, which is kind of retrofitted and can cause congestion. And Zen is that modern traffic system with flexibility built in from the ground up. And that's really the point of this presentation. Are there any questions? I'll be here the rest of today. I'll be here tomorrow. Connect with us on LinkedIn. Thanks for the emojis there. Connect with us on LinkedIn. Come to the website. The website, as with most projects, is always a work in progress, but we've added some really exciting things to it. We have the Zen Summit coming up in September in Silicon Valley. It's hosted by AMD and Xilinx. It's going to be an amazing event, September 15th to 17th. It's probably a little short on timing for folks, but you're more than welcome to come. We'd be super happy to have you there. And I'll keep you informed about the next summit coming up. Zen is going great places. We want to see you there. I'd be happy to answer any questions. If you don't want to answer questions, ask questions right now. I'll be around. Do reach out to me. Connect with me on LinkedIn. We can chat about it privately. Honestly, I prefer to chat face-to-face rather in front of a group, but I'll take any group questions if there are any. I appreciate your participation, for being here. What a great event that we have today. Any questions from the audience? DOM 0, really, if you think about a traditional data center hypervisor, you can connect and spin up new VMs. So DOM 0 is that interface that allows an application, it's usually a web app, that the administrator can connect to and say, I'm going to give you a new VM. They use an application that communicates through DOM 0 to create new VMs. So the difference is in embedded space, you have a fixed number of VMs. Actually, I didn't repeat the question for the camera, but the question was, why do we need DOM 0? So in the embedded space, you know when it boots, you need 5 VMs. One for the infotainment system, one for the engine, one for the braking system, one for the climate control, making these things up as I go. It's fixed. So we can have a configuration file that defines all the VMs when it boots. Or in a dynamic use case, if you have like a data center or an on-site data center, DOM 0 is that interface that lets it create VMs dynamically. To answer your question? Awesome. A question?
Yeah, kind of a follow-up question.
So the question is, in a DOM zeroless environment, if a VM crashes, how does it know to restart it? I think there's just some logic to reboot. If you can add that configuration when you build the configuration of the, you can add the configuration when you build the configuration. When you write the configuration, you can add a parameter to say to reboot if the operating system fails or it seems to be frozen. So there's a minimal amount of logic built into the hypervisor. Question here?
Yeah, about DOM0 environment.
Yes.
If you go with DOM0less, you have to specify everything from the scratch.
Yes. The question is, if you go with a DOM zeroless setup, do you have to specify everything from scratch? Yes. So you'd probably copy a configuration file from somewhere else and customize it, but yeah, you need to have a fixed workload in a DOM zeroless environment.
What happens if you want to add something afterwards?
That's a good question. I don't have the exact answer, but I assume you can modify that configuration and restart it. Contact me on LinkedIn and I can ask one of the maintainers to tell you specifically how they do that in the embedded space. To answer your question, more or less. Question? Two questions. Yes?
So does Xen provide any debugging utilities? So if an operating system or virtualized environment fails, can you debug why it failed and so on? Does it provide any serial output? Does it provide any debugging utilities to find out why it crashed? And then my second question is it possible to run multiple DOM-zeroless Xen machines and then have one master plane that controls all of them?
So the first question is, can you repeat the first question? Is it what are the debugging tools, and how do we debug if something fails? The serial port is the first place, and that's how the tests run in the CI. So when custom hardware is being tested, the host computer connects to the custom hardware through the serial port, and if something fails, we'll get stack traces and dumps on the serial port to debug that. More advanced debugging tools, I don't actually contribute code to the Xen project, so I don't have the actual debugging tools that make it work, but I can get you that information without any problem. I don't want to approach the speaker there with the microphone. I can give you more details, but I know that they test the CI uses the serial port for debug. And the second question was, can we have multiple DOM zeroless environments with kind of a main control plane and secondary planes and have them communicate together? In theory, yes. I don't know if anybody's doing this today. I know the people to reach out to find out if that's the case. But like many of the projects being built right now using virtualization technology, they use virtual I/O. Vert I/O is the interface in between machines. So I assume this would work in that use case too, right? Vert I/O to communicate between multiple DOM zeroless environments. So I know I'm not answering your question exactly because I don't have the exact response, but connect with me on LinkedIn and I can get a more detailed answer from the maintainers. Is that okay? Thank you. Other questions? Thank you, everyone, for your time. Thank you for your participation. I think I'm right on time. Thanks, everyone. Appreciate you being here. Enjoy the summit.